Hi, Amanda, Nadia.
Hi, Lola.
Hello. So are we all here? Is Mehdi there?
No, we still miss Mehdi and Jeff.
Okay. Okay, so we're still missing Jeff. I'm just going to maybe just introduce you to, we wanted to do like a quick presentation, like everyone introduces themselves. So this is Nistor.
Hello, everyone. So my name is GROZAVU. So I'm the president of the jury, and my domain of research is machine learning. So I'm a member of the lab.
Nice to meet you.
Okay. So yeah, you can go ahead, maybe.
Myself.
We cannot hear you, Nadia.
Can you hear me now? Can you? I can hear you.
Je pense que c'est le.
C'est
Peut-être
lequel?
comme ça, c'est moins bien, mais au moins ça marche.
Je connecte.
Non, je pense que c'est le câble qui est cassé en fait.
Qu'est-ce qu'on fait?
On met
Notre câble?
si vous voulez.
Ouais, attends. Quelqu'un avec ça.
Merci.
Yeah.
Tout va bien. C'est bon? On est là, je crois. Non, c'est bon. Ah, normalement, oui, je pense.
Can you hear me now? Can you? Okay. Okay, so nice to meet you all, and thank you for inviting me. So my name is Nadia BERTHOUZE. I'm a professor at University College London, and I work in the area of affective computing. Amanda, maybe?
Hi, I'm Amanda Williams. I'm a professor of clinical health psychology. It's very good to be here for this PhD defense. My specialism is the psychology of pain.
Thank you. Marwen.
Hi, everyone. I'm Marwen BELKAID. I'm happy to be here. I'm a junior professor here at University, and my research is on decision making and emotion. Nice to meet you all.
And well, everyone knows me, but I think Lola Cañamero, I'm a professor here in the chair of neuroscience and robotics, and I am the lucky supervisor of the week. And we're still waiting for
Problem. I will send you back.
who seems to have a problem with the link, and Mehdi KHAMASSI is the manager. I'm gonna check my Zoom to see.
Il est là.
Il est connecté?
Ouais.
Et Jeff, non?
Pas encore arrivé.
Bonjour, désolé, j'ai dû tout réinstaller Teams.
Bonjour, on n'est pas encore.
Maybe.
Oui.
So we were just doing like a round of very short introductions in the panel. So maybe we wait for Jeff and then Jeff and yourself introduce all of
Sure.
them.
Yep.
Oui, le lien. Ouais.
Il ne l'avait pas?
Et je lui ai envoyé ce système, il a dit que.
Ah, d'accord. Ah, ça marche pas. Ok.
Oui. It's like. Jeff, tu veux enlever tous les slides, ça m'empêche d'accéder à tout. Ok. Ouais, c'est bon. Tu peux. Oui. Tu peux activer le micro et moi je vais le désactiver. Ok. Oui. Ah oui, c'est bon.
Let's come back to that, everybody. Hello, so I think we are all here now. We were just doing a kind of a quick round of very short presentations, so we'll repeat again what we had done. Okay, Nistor.
Nistor GROZAVU, so I'm a full professor at Cergy Paris University and working in machine learning. So I'll be the president of the jury of the thèse.
Okay, Marwen.
Nice to meet you all.
Nadia, do you mind introducing yourself again?
Sorry, what did you say, Lola?
Yeah, do you mind introducing yourself again, because there's new people who
Oh,
are
okay, no problem, no problem. So I'm Nadia BERTHOUZE. I'm a professor at the University College London, and I work in the area of affective computing.
Thank you. Amanda, sorry, would you mind introducing yourself again?
Sure. I'm Amanda Williams. I'm also a professor at University College London in the psychology of pain.
You, Mehdi?
Yes, hello everyone. I'm Mehdi KHAMASSI. I'm a research director at CNRS and working at Sorbonne University. I'm working on decision making between neuroscience and robotics.
Thank you. Jeff?
Hello, everyone. I'm Jeff KRICHMAR at UC Irvine. I'm a professor there, and my interest is in cognitive robotics and neurorobotics and computational neuroscience. Nice to see some familiar faces.
Yeah. Thank you very much. And well, I'm Lola, I'm a professor here at Neuroscience and Robotics. I'm the supervisor of Louis, and so I think we can probably now.
So we'll start the thèse de défense with L'Haridon. Donc, pour dire en français, la douleur, le plaisir dans la boucle émotion-cognition, les robots en tant que modèle. So 45 minutes for the presence and then we'll move to discussion and questions.
Thank you very much. Share my screen. Yes, so no. And slide didn't work. Ah. Yeah. Okay, great. So, hello everyone, I'm L'Haridon and I'm there to present my thesis defense. I would like first to thank the jury who accepted to evaluate this work. So, in the first time, I will give you some background about my work and why we do this. I will then present you in 4 different sections, the different parts of the work that we've done on pain perception and sensation, on modulation of pain perception with cortisol stress, and embodied sensory representation and representation in interaction, on influence of the social context. And then I will give some discussion and takeaways of this research. So, just to give start, this is me. I was 3 years old. I was my first experience of pain, and I had absolutely no idea of why pain should matter in robotics. And now I'm an adult who has spent the last 3 years of my life to study action selection and how pain mechanism can affect it. So action selection is the idea to make a decision regarding which behavior to execute next to achieve goals and survive. It works for biological agents and also for autonomous robots. And this process of action selection can be modulated by affective processes such as motivations or emotions. We will focus to work on the idea of embodied AI. That will be our paradigm for this test. The paradigm of embodied AI is the idea that the intelligence emerges from interaction between agents and their environments. And that's where we get intelligence. For example, we can get complex phenotype of behavior response using small architecture that use actuators. That's the example that has been done by Brooks with the subsumption architectures. We will work on motivation-based architecture, which are ethology-inspired action selection architecture, which build on some work from Damasio's that work on the different representation of level of automated homeostatic regulation, the idea to maintain physiological variables within a permitted space. And Lola Cañamero did a first work to propose architecture based on motivations that work on the idea that you have an internal physiology, you have stimuli that both goes to compute motivation that selects the correct behaviors. And motivation allows us to make reactive architecture more active. So if we go to study what is the definition given by the International Association for the Study of Pain, we can see that pain is an unpleasant sensory and emotional experience associated with or resembling that associated with actual or potential tissue damage. What is important is on this definition, the idea that pain is a sensory and emotional experience that is linked to actual or potential tissue damage. They added 6 keynotes to this definition, which gave us a lot of interest. Pain and nociception are different phenomena. Pain cannot be inferred solely from activity in sensory neurons, and a person report of an experience as pain should be respected. So what is nociception? Nociception is the pain perception pathway that gives from first when you get an injury on an arm, that's my brother Florian, which has been injured. You get peripheral nociceptors everywhere in the skin with different layers of sensors in the dermis of the skin that goes up to the spinal cord, that goes up to the brain, and that gives a pain emotional experience that is redistributed via the spinal cord to the different parts of the region, so you can get the feel of the pain. But pain can also happen without injury. Pain can also happen if you are amputated and you get no leg. So that's a phenomenon of phantom pain. So pain is an experience that is not only linked to a real physical damage, so it can be seen as a global experience. Our approach, when we compare that what has been done in the literature in the field of pain modeling, there are multiple researchers that focus on the idea of modeling the sensors of pain. Approach by Jung to do a memory store approach to rebuild nociceptors, artificial nociceptors. Parvidi and Fard propose a sharpness sensor. Sharpness is one of the features of the nociceptive pathway. Abdelwahid proposed an artificial skins. And there have also been some computational approach, like the one that has been done by Maniscal and Fantino, that focus most on the computational neuroscience perspective. But we will propose to have an approach to see pain as an experience that is not only related to damage, that is different from purely nociceptive. So the objective of this research is how can pain be modeled in robotic systems to influence action selection? What are the neurobiological and behavioral foundation of pain perception that can apply to robotic architectures? And how do this model contribute to embodied representations in robots? So this is an eye view, a diagram of our model with the different sections that we will discuss in the next minutes. The first one, we will propose to study the adaptive value of pain with a behavioral perspective to modulate action selection. In the second time, we will study some temporal dynamics with a neurobiological approach to modulate pain perception. We'll then work on the learning of embodied sensory representation, integrating a biologically inspired sensory inputs and some computational neuroscience perspective. And then we will discuss the influence of the social context, proposing an action selection model that integrates all of these perspectives. So let's talk about pain perception and action selection. The question that we can ask is, what is the adaptive value of pain? We can see that in ancestral environment, pain is closely associated with survival threats. You get a predator that will attack you. and that is related to actual physical damage. But in modern environment, pain does not seem so causally related to survival-related threats. You are not attacked by lions in the streets. And that does not necessarily have a strict correlation with physical damage. You get chronic pain that is experienced without any physical injury. So we will propose onboarding this to study first to use a model of action selection, to propose a model of artificial nociception, to propose a model to compute pain perception using this artificial nociception, and to evaluate how different levels of pain perception can influence action selection. So this is the two resource problem, the problem that we will use. So you have a robot, an agent, that need to evolve in an environment that need to consume two different types of resources in order to maintain its homeostasis and to survive. So here the agent is a robot Timio2, he evolved in a wooden arena with different tiles that represent the resources. So you get a physiology, a motivation-based model that is based on physiological space, tegument, which is the soft skin, like when you are a duck, for example, you get tegument, temperature of the internal temperature, and integrity. These physiological variables are linked to sensors. So grooming spots can be detected, energy resources, and dangers. You have then motivations. I am hungry. You have grooming. I want to groom, and I want to avoid danger that lead to behavioral systems that are related to the motors. So to give a detail to the architecture, first let's see physiological values. A physiological value is a value that fluctuates as the robot moves and interacts with the environment, that is defined by an ideal value, an actual value, and a deficit. And you can see the formula. So these are the basic of our internal physiology. You get motivations, or the wanting to act, that are computed using both the deficits of the related physiological variable and the cues and the perception of the environment. And to select the correct motivation, we will use a winner-takes-all architecture where you get multiple inputs, and the greater input give you the output that is selected to select the related behavior. For the behavioral system, we will have multiple types. The first one is a seek and consume that we built using a subsumption aspired behavioral system. So you have different levels that are selected within the sensory information. So you can wander, seek, or consume information. Wander is the environment. You see a resource, you seek to it. You can consume a resource, you consume to it. And you have a more reactive avoidance behavior that is based on the Valentino-Breitenberg vehicles with the following equation. For artificial nociception, we propose the first novel model that integrates two types of noxious stimuli, because in nature, nociception is related to multiple types of stimuli: temperature, pressure, scratching, toxicity. So we propose to use, as we have a robot, a model based on impact and not scratch. So for impact, simple. The more an obstacle goes quick to the robot, the more the impact is updated. And scratching is based on the scratching around the robot, like it can turn around. So then, when we get this, we use some spatialization feature, which are called the pain irradiation principle. That we use a Gaussian, and that is a feature in the biology where when you experience pain somewhere, it radiates to the neighbor area of the skin. So we wanted to reproduce this feature. So that gives us a small demo that show within this how we can activate and integrate our nociceptor features in real time. We then will compute pain using an artificial hormone. An artificial hormone is something that will increase or decrease based on a gland that is excited by something. We will use nociceptors on the base excitation of our gland and different mechanisms to compute. So the gland is related to damage, and you have different types of computation that can lead you to select the correct to select the level of hormone. So you can use something with a memory and a decrease rate. We can use, for example, a mean concentration, or we can also use a direct correlation between a direct relationship between the gland and the hormone. We wanted, as we can see in the different time perception, we see that here you lose less information because you keep in memory, so you get greater recall. So we selected the memory hormone to our nociceptors. The question that we ask, that we think about is it still adaptive to experience pain nowadays? So we will play with this alpha parameter to give multiple perspective hypocorrelation between damage and pain, standard correlation and hypercorrelation. So an hyper perception of pain or an hypo perception of pain. So we will use these parameters to fluctuate it. We use then another parameter of the another feature of the pain in biology, which is called the second pain principle. You have, when you get it, first high and intense peak of pain that is followed by the second long-lasting and lower, like burning pain perception. So we wanted to reproduce it, and we integrated it in our model of pain. We add pleasure hormone, which is related to well-being. Well-being is like the overall satisfaction of the physiological variable. So the less the deficit are, the more the deficit are low, the higher the well-being. So you use directly the well-being to compute the gland of the hormone, and we use the same formula we use for pain with decrease rate and decay. So what will be the impact of pain and pleasure on our action section model? Pain will affect motor strengths to get you that when you experience pain, you can engage stronger to avoid the danger and to flee. It will reinforce the avoidance motivation, leading you to try to avoid danger. And pleasure will impact and increase the motivation to consume. So the more you're satisfied, the more when you see a resource, you are trustful and you want to go to it. So we will have a task where we will have different type of resource. So with or without groom, that the groom are with or without obstacles on the resources, so that we can see that you can consume a resource. And in some case, in environment with high level of danger, consuming resource will lead you to feel pain, because if you go to groom too fast, you will excite the scratching receptor, and if you activate too fast to the resource, you will activate the speed impact of the nociceptor. So we will have three environments: one with no obstacles and just resources, one with just obstacles on the environment, and the other one with obstacles and predation. In this first model, predation is me, who attacks the robot at a regular timestamp and try to avoid him to attack him a little. So let's study some results. The first is the average lifespan. Lifespan is the number of times that the robot has survived in our model. So so you have a lifespan in seconds, so how many times the robot survives. And we have the three models. So we can see this in low danger scenario. Yellow is no pain. You have blue, green, and red, which are hypo, normal, and hyper perceptual pain. When you are in low level of danger environment, lifespan decrease with increased pain perception. When you are in a medium danger scenario with the obstacles, pain is adaptive in moderation. So having this normal correlation increase compared to no pain, but you reduce your lifespan when you have hypo pain or hyper perception of pain. In the contrary, in higher danger scenario with both obstacle and predation, you see that the more the pain is perceived, the longer the lifespan is. And you get also a second feature is that you get greater lifespan diversity with pain perception than with no pain perception. If you look at the causes of death, so why is the robot dead? Which physiological variable went to a fatal limit that lead to death? When you're in low level of danger scenario, a robot does not die from integrity, but from energy deficit and integument a little, but mainly from energy. In medium danger, you have the first time when no pain is perceived that the robot does die from integrity. And in high danger of scenario, robot consume resource efficiently, even if it causes pain, because it die mostly from energy and less from pain. But in hypersensitivity to pain, you get the first time that it die mostly from lack of integrity. We propose to compare a model to another model, which has been developed by Maniscalco and Fantino. It's built on a soft sensor approach. They use like NAO robot, and they use the idea to use the personal space of the robot to compute their nociceptive activity, when we propose to use peripersonal space with the sensory perspective. So they use two types of pain induction, like us. They use instead of impact massage, they use motor temperature and motor stress. and they computed using computational neuroscience formula a direct correlation between nociceptor derived stimuli and pain. So we did the same experiment that we did with our model with there, and we see that if we compare the difference between damage and pain, in the up it's our model, and in the lower it's their model. Pain is present with higher and more intense peaks with their models than with ours. Threshold, there is a threshold effect because they use like a filter in their model that see that for us we get small wave of pain, so small perception of pain, and then it's only big peaks and not only then, and you have an exponential computation in their model that lead to saturate quicker than our model, so they get higher and more intense peak, as we can see. If we compare the causes of death on the lifespan, we see that with their model, the robot tends to die more often because of lack of integrity than with us. And the lifespan is slightly lower, but quite similar in perception that with us. But we get standard derivation that are more similar between both conditions, so we kind of reduce variability than with our model. So to discuss the first part of this section, the question we ask is it still adaptive to feel pain? We propose a study of a different level of pain perception influence action section. We propose a model of pain perception with spatialization and temporal dynamics drawing from biology, and we compared our model to another model from literature. We saw that hyperacuity to pain is adaptive in extreme hazardous environment, even if the conception of danger can lead to damage, because in this environment you have obstacles. So when you consume obstacle, plus if you feel pain, your motor action is stronger, so you will engage quicker and more intensely to the obstacle. So you will experience damage, but that leads to a better, and that insensitivity to pain is more advantageous in environment with less danger. That result highlight for us, in our point of view, the adaptive value of pain in dynamic environment where an agent needs to actually escape danger. In this next part, we will work on the modulation of pain perception. So the question we wanted to ask is how to improve survival in environment with predator-related danger. So resource-seeking behavior can expose agents to risk in nature. And one of the primary sources of stress and pain is a threat posed by predator in an environment. And pain is modulated by different hormonal processes, such as cortisol, which is the stress hormone. So we wanted to ask some question. How does the integration of stimulated cortisol influence action selection in robots with pain perception? Can a hormone-modulated pain perception model improve the adaptability and survival range of robotic agents in dynamic environments? And how do temporal dynamics, such as delayed pain response and hysteresis, affect the robot's ability to navigate and adapt to different levels of environmental stress and predation? So we will propose a model of simulated cortisol, modulate the robot pain perception with this simulated cortisol, and evaluate and assess model performance in different stress-related environments. So this is our new robotic platform, KPRA4, which is a more complex Swiss-made by K-team robotic platform that has IR sensors, US sensors, ground sensors, and camera, and a small computer on board. And that's the robot that we will use now for all our next experience. So as we can see, we have updated our model with now 2 physiological variables, energy and temperature. Different sensory, and you can detect shade, food, obstacles, and select the motivation, eat, cool down, avoid. So motivation, temperature increase with time, so you need to get some fresh air. Energy lower, so you need to eat to increase energy. And you have the related behavior system. So the objective of the task is still a 2-resource problem, but in a square environment with different types of resources where KPRA need to evolve and to consume the related resources that is linked to the physiological variables, so shade or food. We propose to compute model hormone. So first, we work on the idea of comfort. Comfort is linked to the idea of still the reducing the deficits of the robot. We then propose to compute an simulated adrenal ground release rate that is based on both internal comfort and external discomfort, and external comfort with the nociceptor of activity. So you get a stress hormone that is linked to internal and external perception of the environment. And you get then cortisol concentration that is built on this release rate and decay, still using the same formula. And we also propose the second mechanism for release rate So first, first it can be related to intercept, and we added a negative feedback where the previous level of cortisol concentration will influence the next release rate of hormonal concentration, so that will lead us to compute and to analyze with a memory of past experience. So stress cortisol will affect the science of environmental cues, external perception. When you're stressed, you see an analysis swing stronger, more intensely, and pain still affects the motor strength. So we have these two setup problem with different with the following setup. We will make vary the number of predators. We will use Timio not as adjunct but as predators. Timio can have 3 types of predation: stalking, so they wander around the environment, and when they see the agent, they attack. Actively hunting, so they go quick in the environment, searching for other predator. And constant, which is every X seconds, I induce damage to the agent. So the idea is that we have a task that lasts 600 seconds, or less if the robot dies. And we will do 5 rounds for each condition: damage correlated, cortisol modulated, and cortisol modulated with negative feedback. If we look at the viability, which is the survival rate for 600 seconds of our model, we can see that cortisol modulated pain perception gives better survival rate in all number of predators and all type of predators. And negative feedback further enhance this results in interval lifespan. We can see it, for example, with a stalking predator where you get 20% of increase. If we look at activity cycles are the evolution of deficit over time as reflected in the physiological space. The physiological space is if you get two physiological variables, a 2D space, where you can see evolution of the deficit. But if you get 3, 4, 5 physiological variables, you can get an ND physiological space that defines the internal value of the internal physiology of the robot. So if we look at these activity cycles, we can see that without cortisol and with cortisol, deficits are more balanced with cortisol modulated pain perception. For example, you can see that just there, they went out of the permitted survival rate, which means that a robot correctly balanced its internal physiology. Negative feedback, you get an increase because if results were maintained quite high, they reduce around time and lead to reducing the deficits closer to 0. So negative feedback further improves this balance management. If you look at the intensity of cortisol, you get scenario with 0 predators and 2 predators, with on the left cortisol modulated pain perception, and on the right with negative feedback. You can see that when there is no predator in the early life, there is kind of a mechanism of desensitization. So you can still encounter stress when there is no negative feedback. Acute negative feedback, having low stress in early life, leads to maintain a low level of cortisol all around the life of the robot. In the contrary, in an environment with higher level of stress, you can see that it quite fluctuates when there is no negative feedback, but there is a sensitization mechanism where if a lot of stress is encountered in the early life, cortisol level remain quite high in all during the experiment. We also were able to observe different emerging behavior. So we can see that in this model that we have like a quite defense against the predator's behavior that will so the robot turn. We can see the Brighton bear moving, and then we now attack the predator where it's programmed to avoid danger. He shocks them twice. In the contrary, with negative feedback, you have like this laziness behavior where you don't wander around the environment, you just stay close to a resource until a predator tries to attack him, but then he still stay quite close to the resource. So we can see like quite laziness, hedonic behavior where he stay close to a resource. So we ask ourselves how to improve survival in environment with predator-related danger. We study an influence of how cortisol modulated pain perception and robot behavior in varied environments. We did some experiments to assess the impact of cortisol on viability in these two resource problems. And we see that cortisol modulation of pain enhances adaptability to stress and danger in both number and type of predator in our environment, in our specific case, but that cortisol-modulated pain perception improved survival rates and management of physiological variables. So now we wanted to work on the embodied sensory processing and representation in interaction. So the idea is that touch, how to reconstruct and learn sensory representation with robots, because touch is a sensory modality that's essential to perceive and respond to physical contact. But it involves specialized receptors that detect mechanical, the mechanoceptors, and noxious stimuli, the nociceptors. But robot does not have these specialized receptors. So how can we reconstruct? So we work on the idea to create an adaptive sensory field to simulate complex tactile information. We propose to develop a robot model that integrates both mechanoception and nociception. And in collaboration with another scientist, Raphaël Bergouin, we propose to add a neural network that processes this sensory data akin to human somatosensory cortex and anterior cingulate cortex, which are responsible in the brain for both where and how we are touched. So the idea is we take, in the nature, you have different mechanoceptors and nociceptors, but our robot, he has only proximity sensors. So we first try to interpolate the proximity data, then we visualize them in a polar coordinates. We see that some kind of blob appears. So building on this, using a Cartesian representation, we built and proposed a sensory field. And using this sensory field, we send information to a neural network that has been developed by Raphaël Bergouin. So for the mechanoceptors, we wanted to reconstruct in the human body that detect touch, frequency, velocity. We wanted to work on both how you are locally stimulated. So we visualize the sensory body as an elastic material. We use Hooke's law functions to reconstruct the force applied. Then using our shape, we can compute strain and stress. And building on this, you can get the Young modulus that is both an information that computes or locally your touch, and now globally the sensory field is deformed. So that gives us a mechanoceptor for in all point of our robot and how the sensory field is deformed. For the nociceptors, we use this data that are linked with a different threshold to detect and interpret data. So we analyze first the force applied. Building on this force, you can see that if touch or not. We analyze globally the form to detect if it's an intense, sharp detection or a more diffuse, more global type, and we classify. We then compute using the force applied if it's we can compute the velocity of the touch. Is it a quick, high velocity or a low velocity touch? We can also get the touch events from which we can compute frequency, and then if we have frequency, we can have low frequency, high frequency. And finally, we can get the duration of the touch. So is the contact long or not long? So we have an 8-dimensional vector that represents and characterizes how a tactile stimuli is reconstructed. We did an experimental setup where I simulated Kepera around the table during the 20 minutes. We did 5 times, and we stimulate every sensor under every condition. What we can see in the network dynamic, so you get like the SPAC activity real time, is that you can see that neural network show distinct dynamic during learning. So you get different pattern activation. Neurons associated with mechanoreceptors in salmon responded earlier than those with nociceptors. That can reflect a feature in biology, which is the difference of transmission footprint between beta and delta fibers that are the link between the nociceptors and the spinal cord and then the brain. If you look at the weight connectivity, so how each neuron associates to each other, we can see that learning led to the formation of modular structures in the neural network. We get strong connection formed between neurons associated with the same sensory receptors, so mechanoceptor and nociceptor, somatosensory cortex and anterocingulate cortex, and that the network exhibited a ring connectivity like a torus. That means that robot has learned that it is circular, so that the first and the last sensors are connected and are neighbors. So that was an interesting result for us. We can see there a live demo. So this is me exciting the robot. So you can see that different types of contacts are induced. You get mechanoceptive and nociceptive features that are computed in real time. The tactile information are set to the neural network, so you get the spike activity. And you can see that weight connectivity forms with the segregation of different cortex area So we asked ourselves, how can we how to reconstruct and learn complex sensory representation with robots? Our model successfully captures complex sensory information, including noxious stimuli, from very limited sensory inputs, and it highlights the segregation specialization of different brain regions, which can be used for different tasks. So in last section, we propose to study the influence of social context. So how different social contexts can affect action selection. Body awareness and how we perceive our body significantly affects the pain experience. Pain perception shall not be exclusively a sensory experience, but an embodied one, shaped by how the brain integrates these sensory inputs with cognitive and emotional states. And different early life interaction can result in different developmental trajectories, affecting how individuals perceive and experience their bodies. So how does embodied sensory representation influence pain perception and action selection in a robotic agent? How do early sensory experience and social interaction shape body awareness and influence decision-making in robots, especially in the presence of social contacts, predatory threats? So we propose to integrate sensory field to our action selection model that we proposed in the last section. We integrate also the learning of embodied sensory representation in the pain perception. And we study how different levels of social interaction with predators influence the construction of a body representation and how this will affect the action section. So this is our model. We propose then 3 physiological variables: glucose, water, integrity. And then you will get different type of external cues: water, food, nest, where you can reconstruct integrity. So we propose a new navigation algorithm to replace the Breitenberg reactive behavior that is built on our sensory field. The idea is to compute the centroid of the deformation and to minimize deformation of the robot, so that leads us, because Breitenberg is like a robot that turns a lot to a robot that turn less and that get more adaptive and that can more move to avoid predatory threats. We propose to add another mechanism that highlights the central role of cortisol in our pain perception model, which is called the gluconeogenesis. So the idea is that we compute still well-being using some error, maximum error to compute the level of well-being. From this, we compute the release rate of our cortisol hormone that is based on damage, on a previous cortisol level, on pain level, and on the well-being level. And we get cortisol level that influence the glucose level. So cortisol influence is a mechanism in biology that is called gluconeogenesis, that when you're stressed, you get more energy to respond. So being stressed gives you quite a bonus to also survive better. So we worked on our pain perception model being an embodied perception based on both internal and external stimuli. So it's built using internal sensation of the cortex and cortisol, and cortex activity will influence pain perception. We have a model that works at 2 different time scales because a spiking network run at higher frequency than an action selection model. So we have mechanism of accumulation of spike events to compute different formula, and well-being reduce pain while cortisol increase it. So we have now our 3 resource problem with food, water, and nest. We have 4 types of predators. We added a new type of predator, which is early life. So damage is induced within the first minutes of life, and then it stops. And we also have added force predators to a number. If we look at for neural dynamic during experiment, look, for example, early life predator scenario with no stimuli phase, you can see that you still have mechanoreceptors and nociceptors that respond with different network dynamic. You can see that you get navigation impact because the robot will move with its head. So you can see that mechanoreceptors from this part from this area of the brain are more activated. And you still get, when there is no stimulation, this memory recall that highlight that the network learn its embodied sensory representation. If you look at the weight connectivity still in the early life scenario, you can see that you get stimulation from 0 to 5 minutes, and then no stimulation, and then again from 12 to 15 minutes. And connectivity is not lost. Connectivity of the different neurons is not lost during this non-stimulating phase, and areas are still segregated, and the ring connectivity still appears. We also wanted to compare web connectivity in different conditions. So you can see the results of construction after different learning time and conditions differ. You get on the left 0 predators 15 minutes, and on the right 5 minutes only, but 4 predators. You can see that you get a partial representation with a part of the sensory that is not learned, and in the other side an over-connected representation, which can highlight that different experience of life lead to different developmental trajectories and different representation in the brain. We wanted also to study the intensity of cortisol. So in the up, you get no cortex, in the down cortex, 4 stalking predators, early life predators, 2 stalking predators. So with 4 stalking predators, you get an high stress scenario. With no cortex, you can see that cortisol is increased quite constantly. But with cortex, it's not a scenario where you get constant. It's a high stressful scenario, but it's not a scenario where you get constant induction. So adding the cortex allows us to get cycles where when there is no damage induced, the cortisol level decreases. In the contrary, in a lower stress scenario with only 2 stalking predators, you can see that without cortex, the level of cortisol is quite fluctuating, while with cortex, you get a more stable evolution of cortisol over time. And during this early life predation, you get a no-stimulating phase. So you can see that there is a forgetting of the stress past experience without cortex, and there is a memory sensitization that appears with the early life predation. So we ask ourselves how different social concepts can affect action selection. We propose to integrate embodied representation, combine hormonal modulated action selection with embodied sensory representation. We integrated nociception and mechanoception into our action selection model. We propose to study the impact on survival and adaptation, adding bio-inspired cortex to our model modulation and how it improves survival rate and activity cycle performance. We see that cortisol regulation led to smaller and finer adjustments, incorporating bodily memory for improved adaptive response. And we see that in poor social context, no predators, sensory representation learning is limited, while in rich social context, multiple predators, we observe the segregation of features in the cortex, and we'll see that we learn complex sensory representation that enhance survival. So to give some discussion and takeaway about this thesis work, just to highlight the major contribution we did in this thesis, we propose to study the affective element of pain as a modulator of action selection and behavior. We propose to study cortisol pain interaction and its influence on decision making. We propose the model of artificial nociceptors to process noxious stimuli for mobile robots. We also propose to study tactile representation framework with a sensory fit for more complex interaction modeling. We also integrated neural network spiking, which built this embodied sensory representation. As takeaway, we saw that pain balance action with survival versus resource-seeking behavior that need to be selected. We see the adaptive value, particularly the hypersensitivity, which is useful in dangerous settings. We see that cortisol modulation can lead to fight or flight or laziness in different environments. We see that hormonal memory can drive us to habituation or sensitization. We see the neural segregation of different areas leading to mechanoceptive and nociceptive features. And we see that early sensory interaction shapes the sensory representation and the behavioral adaptation of our model. We, for this thesis, published in 2 international conferences, ACI 2003 with an article on the effect of stress on predation and pain perception, on SAB 24 with the emergence of complex sensory representation. We also presented in a workshop, in an international workshop for ACI 2022. We are working on 2 new journal articles. And to give some perspective to what we did in this work, we propose we can work on more complex sensory inputs because Kepera has quite limited sensory inputs. We can work on different frameworks. We can study the dysfunction of pain perception. You have chronic pain, you have also phantom pain. What happens if you lose a member or part of a robot? You can also work on the troubles of body representation, dysmorphia, anorexia, which can lead you to different pain perception and different behavioral response in interaction with the environment. We can also study hormone in positive interaction, oxytocin, which is linked to affective bond. we can also study more the interplay between pain and pleasure, because pain is not the opposite of pleasure. They are both different and separated emotional experience. We also could study positive social context. We study a lot predation, but what happens if you get a family of robots, because pain has some social features, it propagates, it is a social experience, an emotionally shared socially experience. And we could also evaluate the frugality of our approach by computing, by calculating computational costs and then carbon footprint, and how our model can differ in a performance than others. So I want to thank you all, and I am now available to respond to your questions.
Thank you for the presentation, the clear presentation, which is complementary to the book. So we can start the second session now. Second part of this difference, which are the discussion and questions. And we start by the reviewers, and we start by Madame Nadia. Some questions.
Elle a son micro coupé.
Public class.
Nadia,
She cut her mic.
Nadia.
She has mic turned off.
you're muted.
Yeah.
So we said that we start the second part with the questions, and we start by you. If you have some questions or some remarks.
Okay, so I'm the first one. I heard Amanda first. So, okay. So first of all, I'd like to say we did incredible work. So it was really very interesting to read, and I think is you have explored many different mechanisms for this incremental work. So really well done, and a nice contribution to various fields, not just robotics. My question is, so one question I have is, how does it, if you could elaborate a little bit more in terms of how your work differ with related work. You have shown few at the beginning. You did also some comparison in your first study chapter, and I wanted to ask, who are your competitor, and to what extent your work is going beyond that or compared to that, in addition to the one you have already presented in your slides and with the first study chapter.
Okay, so first I think that we differ from approach with other competitors, because I would say that in this kind of field there is very few study on how this specific affective processes, which is pain, can affect action selection. So we said that there is multiple people that work on sensory representation. We worked on sensory representation, but most of the people try to build new sensors to assess and respond to the physical stimuli, to the noxious stimuli, to detect sharpness, to detect pressure, temperature, toxicity, and to add them to robotic platform, where we stand in our point of view to say how can we use actual robotic platform and integrate from their sensory information to our model. In the next part, from people that computed this pain signal, this damage signal, I think that very few of them use pain as an affective experience in robotic model. There have been models that try to compute the neural signal that is related to nociception, that is related to damage perception, but there have been very few studies that added this pain as an affective state in an action selection model. So I think that we try to compare to what could be compared. So for example, we found this article, Maniscalco and Fantino, which is interesting because they use artificial nociceptors, but I still say that they use personal space, while we use peripersonal space to compute on nociceptors. And I think that while they propose artificial nociceptors, they didn't propose to integrate and to use this model in an action selection model. So they focused more on computation of the signal, where we try to evaluate and develop on how it can affect action selection. So I don't know if that answers correctly your question.
Okay, thank you. That answered my question. You already touched more in also on the slides. I was wondering how transferable are your findings to other experimental condition and platform, or even real scenario if your some of your mechanisms are integrated in a platform for particular issues. So I don't know, rescue, they have to deal to survive, to be able to contribute to a rescue action. So how are you sure that what you discover in your result transfer to other, you know, somebody repeat your work with the same platform or new platform and conditions?
I think that's what is complex when you work with this much dynamics, because our model is quite dynamic with a great internal dynamic, and we had a lot of this nociceptive value, this hormonal level that gives a big dynamic of the model. So that's why we try to propose an incremental study where we modified step by step, section by section, part by part of the model, and we try to not remodify everything. But I think it's quite complex to compare to other things because we work with real life robots. So we work with varied sensory inputs. So if you vary the luminosity condition of the experiment, you can get a diversity of response. So to try to work on the validity of our response, we try to focus to do the experiments on specific time range where luminosity variation were few. We try to compare the most point points and to really iterate section by section. But I think that that's quite also what is good with the magic of working with embodied AI is that intelligence also emerges from specific conditions, from specific interactions. So we need to propose a framework that can respond to the dynamic of the environment. But we know that if predators are positioned differently in multiple runs, you get a complete different phenotype of behavioral response. So that leads to our specific. When we show the different emerging behavior, they can be seen also as a response to the specific dynamic of the environment. And I don't know if I re-put the same experiment now with the specific life function that we get now, I would get the same behavioral response. But that's also what is interesting in studying a dynamic model, and that gives us to create a wide range and possibility of response to various conditions. So I think that that's why we try to add some number of experiments to assess lifespan, cause of death. But when you look at the specific details, you can see that you get a variety of possibilities.
I'm not familiar with the field. I'm just curious because in your study you don't use, for example, any statistical analysis to see, and I wonder if there was a reason for that. It's like it's not appropriate in this situation, or are there other reasons why you didn't try to evaluate your result from that perspective?
Yeah, we wanted to work to elaborate and to study the more possible the dynamic of our model, and we did limited statistical study because we study a survival rate, the average lifespan, the standard deviation. But what we try to focus more is to see what our model can produce as result as behaviors and how pain can improve in specific dangerous environment or non-dangerous environments. So that's why we focus more on qualitative study than quantitative study. And I think that for our model also, because we work with real life robots, we could extend the number of runs. But for example, the results that I presented in this section are 3 weeks of experiment, and we could have done more. I think that could be an interesting feature that could be an interesting study to do in the future. But we should probably double or triple the time spent on different experimentation. So we also wanted to focus on qualitative studies.
Yeah. I don't know the time. I don't know if I can have more space for question, or I suppose I don't know how much I have for myself. Yeah.
Yes, you have time.
I can ask one more, then I can pass. So, what kind of application do you envisage of this type of architecture in real world? That's one. And what opportunity do you see for people who study pain in using your platform?
I think that first we do some fundamental research. So we have probably not the best direct to industry application, but if we want to have a world that is more robotic, I think that having these affective processes that affect the emotional, that affect the behavioral response of agents are important, because when you interact with robotic agents, when robotic agents interact between each other, you better understand from an external point of view their behavioral response if you see that there are affective processes behind. So, and I also think that can link to how they can be used to get a better understanding of pain. You can propose people that have pain dysfunctions to have real models that allow them to understand better how what they have physically affects their behavioral response, so that also can give an external point of view of a human perspective in this kind of micro reproduction of biology with this scenario, this environment, and that's why we pointed it in the also perspective that can lead us to study the dysfunctionalities of pain, which are probably not enough studied today, because we still don't get every detail of why chronic pain happen and how it happen and how it can be solved. So I think that we can give models that are reproducible and maybe useful to get a better comprehension of our pain mechanism in human and other animals.
Sorry, just one more question. In your thesis, you mentioned that pain has less value in our society, and so if robots will live in our society rather than in a predator type of environment. We can have predator in our society, but a slightly different environment, the one you use to explore that. So to what point would this kind of mechanism be then useful in beyond the use of your platform and architecture to study pain in psychology, but more in terms of the use of robots for, I know you're doing basic research rather than thinking to application, but I just wonder if you consider that mechanism less important in our society in terms of adaptability, the role the pain play in adaptability. So what are your thoughts in terms of the importance of studying pain architecture from this perspective when we think to robotics rather than the understanding of pain itself? I don't know if my question is clear.
Yeah, I think probably I think I might have been quite too aggressive in my manuscript about the importance of pain in our society, because we built and work on articles by Amanda that try to evaluate and to study why chronic pain happen. And this theory of chronic pain can result from a mismatch between our pain system, which is due to respond to danger, to promote avoidance, recovery, or in some cases, and that chronic pain can be quite related in the fact that today we are not aggressed by predators in the street. But pain is an important signal, and as we see, pain is not only related to damage, it has also a social importance, it has also a social connection. when someone feels pain in front of you, you also get an experience of pain. So it's important if we want to have I would say like quite philosophical or maybe a futuristic things, but if we want to have a society where we live with robots, having this emotion contagion is an important feature, because if you want to connect and to have to live with the robotic agents that are embodied in the society, you need to be able to connect to them, and emotional contagion, emotional perception, emotional affective states are features that I think are essential for connecting to a future society where a robot will be part of. And also, I think that beyond what we saw with predator threats, pain also leads to learn the sensory representation. That's why we try to highlight in the last section and last chapter of my thesis, and that if you don't feel pain, there are studies in infants. If they have pain, for example, for newborn babies, they have completely different relationship to pain than a regular reborn baby. So I think that this mechanism, these developmental trajectories, are important to study and to evaluate in a society where robots can penetrate.
Thank you very much, and again, congratulations for your work. I can pass the stage to somebody else.
Other questions? So we continue the second reviewer, Mehdi KHAMASSI.
Yes, hello. Can you hear me well?
Yes.
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 So thank you very much, Louis, for this very clear presentation, and the manuscript was also very interesting to read. So I like globally very much the approach. I think it's fundamental to study in detail some of the mechanisms underlying emotion perception, in particular pain, and testing this on physical robots. So this I like very much. And you did an impressive amount of work. There are things that for me needs a bit of clarification, so I will ask you a few questions and hope that this can generate discussion. So one first, and actually I wrote in advance some of my questions in my report so that you can think about them and prepare. So yeah, one thing I was interested in is the ethology, the inspiration from ethology, which is something you wrote at several points in your manuscript, but was not very clear what was the inspiration. The only point where I found it, there was an explicit link, was about a particular equation in a manuscript where you compute the motivation as function of different physiological variable, and so an equation saying that the motivation will be equal to the error in that physiological variable plus the error multiplied by a Q signal.
Yes.
But you don't explain why. So I wanted to ask you today. So what kind of animal behavior be accounted by this type of equation that other equations cannot capture?
Yeah, we worked on based on this work on multiple architecture that try to study how different animal perspective and ethology perspective can influence action selection. So I think our main reference is TOBIT-RL, which study different type of architecture and how motivation, drives, action selection, behavioral response are influenced. And he built this work himself on ethologists, because he's not an ethologist, he's a computer scientist, which are Spire and McFarland, which study across this idea of what are the terms that we take, the idea of motivation as the wanting to act in response to both my physiology, which can be seen in Damasio, homeostatic control, different level of automatic regulation. Sorry, that's in the same term. And we also took Damasio.
Yeah.
There is cognition, drive and motivation, and there is the immune response. We also wanted to incorporate this, and which has been done in a previous motivation-based action selection architecture. So there have been the first one proposed by Cañamero in 1997, and in many other studies that have been done after, Lewis, Koss, Orlando Villagarcia, and many other, and Imran Khan, that both inspired in this homeostatic regulation that is the proper of the physiology and a motivation to reduce the deficits.
Okay, so it's much clearer, and thank you for giving this perspective and how you reached this point. Yeah, another question was about some of the other mechanisms related to pain that you took into account, and especially you mentioned in your manuscript second pain principle and damage irradiation. But it was not very clear for me while reading the manuscript whether some previous computational models had simulated these specific mechanisms or not. Do you have any idea?
As far from my knowledge, I've in what I did in my bibliographic work and all my literature review and literature study during all the thesis, I have not found other models that incorporating second pain principle and pain irradiation the way we did with the Gaussian redistribution around different nociceptors, because I think that as I said, people focus more on the sensory perception. So some of the features, for example, radiation can be built directly in sensory inputs, but computationally done in a soft sensor and artificial sensor. I have not found references of use of this mechanism.
Okay, so that's part of the novelty and originality of what you did, and that's super interesting to showcase this on a robot. So now I have a set of questions to try and better understand some of your results. And so maybe you could go to the results of your first experiments. Actually, something that I wrote that, for instance, I didn't quite understand why the lifespan is not smaller on average in the scenario number 3, which is high level of danger, compared to scenario number 2, which is medium environment. Well, that's one among several others.
Yeah, I think that's interesting question, an interesting feature that we have in our result. As you can see, in normal conditions, so in moderation, pain is more adaptive in medium low level of danger environment than in a high level of danger environment. But what we can see is that having this pain that reinforce motivation, that some motivation, that increase the motor response, helps the robot to survive longer, even if there is more danger. So that's a trade-off. That's a trade-off between fight or flight. When you escape the danger, when you because experiencing more pain makes the robot wanting to consume more resources, even if it felt damaged. So that's why it died more for integrity. But it managed to consume resources better, so it survived longer. So that's the trade-off that we had in this specific experience.
But here, between, so let's take the normal pain condition.
Yeah.
Between the medium and the high level, it doesn't seem significantly different, is it?
In the normal condition, between the
between
normal
medium,
green,
yeah,
and the hypopain is blue and hyperpain is red.
Yeah, so let's compare the green between environments.
Yeah, different green between environments. So as we can see, we see that they are kind of in the error range between high level of danger and low level of danger, even if it means it's quite higher in a medium danger environment. So I think that results were consistent within 5. Probably rerunning. We did 5 runs for each condition, but probably rerunning with more condition could help us too.
Yeah. Although I know that robotics experiments take already a lot of time, so cannot have but it's important also to highlight non-significance of some of the results and things that. And in general, I thought, I mean, some of your experiments could have been analyzed. I'm sure you can even get more insights. There are things that you could look at further. Just on this one, the two. Yeah, for example, I was wondering whether you have looked in more details at what were the precise behaviors that were underlying these different lifespans. Are agents with pain on average further away from predators than agents without pain? Same question for obstacles. Are the number of visits to resources different? or maybe the proportion of time where the energy level is close to maximal value is different between conditions and environments? Are these things you have looked at?
There are things that we can look at, and there are things that we can't look at because some of the features, for example, we don't have the metrics distance to obstacles, distance to predators, because a robot has no knowledge a priori of the environment and evolve dynamically without any neither memory or in specific case neither memory or knowledge of his position within the environment. But I tried to when I received the pre-report to plot something. So if you look at the time spent on resource, you get similar results than the lifespan, quite similar, I would say, with less significant variation of standard deviation. So I tried to analyze further in the time that I had some more results, but I think that we tried to highlight and show what were the more significant results of the study. But we could probably add many more because we have a lot of data to study. But the challenge was to try to see what were the more relevant ones to understand the behavior, and that's why we don't have all the data. But we could.
I understand. I thank you very much for taking the time to do this additional figure. Actually, it's very interesting because it seems that then can my interpretation be right to say that then the lifespan mostly depends on the time spent on resource and maybe less than on how many damage the robots received?
Yeah, I think that in the specific task that we had for the first chapter on this section, I think that what we can see is that time spent on resource is probably the main difference between the lifespans, and that's why we have integrity is never, except in one condition, the main cause of death.
Okay, thank you. So I would like then to ask you a question about the model comparison that you did, and I think it's very important to compare with existing models, and that's what you did with the model of Maniscalco and Infantino. But I was wondering, how did you choose the values of the parameters of this model?
Yeah, we did some fine-tuning on the variables to normalize. So basically, what we don't have the same inputs in our nociceptor than in their nociceptor. So I tried to normalize every input, so their computational model can be relevant. But I think that's also one of the limits of the computation is that because they have this approach of neuron dynamics, it can't totally be in every point comparable to our model. But I tried to normalize the inputs of the variables.
And in your experiments, after having tried to fine-tune the parameters of their models, do you find some types of behaviors or situations where their model is very efficient and maybe better than your model, but there are other situations where it's worse and that's why it failed?
I think that when you look at difference between damage and pain, you get, I think, what is the fundamental difference, because they have lower, so they have less pain perceptions. So you get less extreme. Most of the time, you get less extreme pain perception than our model. So they avoid less medium danger, small danger, predators that are in the area but not too close. But because they have really this threshold, this exponential computation, you get these high peaks. So when they are really close to resources, the motor strength, which is increased by the pain perception, leads to avoid quicker the predation and the obstacle. So that also, I think, what led to less good resource consumption, and so you avoid too much, and you also avoid maybe too much the obstacles that are on the resource and the environment. So I think that's what the difference.
That's very interesting. But would you say that in a very different environment where you have very distinct locations for resources and for dangers, then maybe their model could be very appropriate, right?
I think that their model could be appropriate in specific cases. Yes. That's one. That's really a part of the environmental dynamic. If you really split the resource and the danger, because they avoid more danger, that would probably have impacted less the resource management and reduce their integrity lack. their lack of integrity. So probably it would have increased the performance.
Okay, then one thing that I wrote also in my report, I mean, when you move chapters after chapter, so it's very nice because you enrich your architecture and so on, but somehow compared to to really understand the full scientific process, you enrich it too fast with too many mechanisms at the same time. I would have liked to see just the addition of one mechanism. What does it change? Removing another one. For example, you get rid of pleasure. What did it change to get rid of pleasure for you? So what could you say about this globally?
Yeah, I think that's the limit of this kind of study is when you do incremental. I wanted basically between chapters to change everything, but you can't because you need to have references. But I think that we lack some specific results that we would like to explore. For example, I would have to have elaborated on the navigation algorithm that we propose, maybe to compare it to Breitenberg. We don't have a result where we only change a specific thing. So that could be really a further study and further result, and maybe a future publication to compare in point some mechanisms.
I hope you will have time to do it. Would be very interesting to look at. I have to say that I found the sensory field approach to navigation very elegant. So this is very nice. Yeah. And so maybe I will finish my questions, in particular about the experiments about early life stress.
Yeah.
So actually, maybe one thing that was clear also from your presentation. No, I wrote something, but maybe yes. Actually, yes. On slide 70, actually, early life that you showed in the middle with the cortex seems worse than 4 predators with cortex, and similar to 4 predators without cortex. With this idea of accumulation, why is that so?
I think that that's because of when you get 4 predators, you don't get constant predation. But in early life, you get constant touch in the early life. So when you get 4 predators, the dynamic of their environment can make them so you can have your agent that evolve in a. If I just show the slide 10 seconds. For example, if you look at deep dynamic, in this you can have all predators that are, if you look at the left, that are stuck there, and you can have your agents that evolve in this part of the environment and that can access resources. That's also part of the dynamic. While when you are fully in a early life predator, everywhere you are, you will get induced noxious stimuli at repeated times. So I think that's why you get.
Okay. Yeah, because I would have found it very interesting to have the time decomposition independently from the intensity of the exposition. So let's say it's the same intensity, but one is during the whole life, another one is just early life, and another one is late life. And that's one question I wrote in my report, because we could think that in an early life exposure, maybe it's good if later in your life, actually, it's a stressful environment, and worse if it's a peaceful one, and vice versa. Maybe if you are naive during early life, you are better for a peaceful environment later, but you're not that good for stressful. Is it something you looked at, or you can look at with the...
No, I think you point a very good limit of our work and a very good idea that I should have had while launching this experiment, and we should have had these conditions to evaluate totally our model, and that's probably something that needs. And it would have been really relevant to study this that we didn't.
But in any case, you see, your work is rich of questions and generating questions, ideas. So I think that's very positive. So congratulate you for this work, and I'm stopping here.
Thank you very much.
Thank you. So we can continue with the examinators. So we can go with Amanda Williams. You hear us from Amanda?
Yeah, I had a couple of questions, but first wanted to say how much I enjoyed reading this, and it was really very exciting to see some of these ideas tested. And I thought you were ingenious in using the cortisol and using outcomes of overall well-being as well as survival, and very interesting to see the emergent behaviour. So well done. Two questions really. One was, in the 3-resource problem in chapter 6, the one that's on the screen at the moment, you didn't really comment on use of rest. Was that because the robot didn't go and rest and recover, or was it because the results weren't so interesting?
Sorry, I didn't comment on what? I didn't hear.
You didn't comment on the robot using the nest to recover.
Yeah, I think that when I focused to study the results, I was really interested in this idea of learning of different developmental trajectories for the sensory representation, that I wanted to focus the study and the result that I wanted to highlight and show on this part. But having this nest resources, the resources could also elaborate to a solo study to evaluate how you can recover and how pain can promote recovery, and how different mechanisms related to pain can promote recovery. But what I was fascinated about and I wanted to study was this idea of developmental trajectory. So I think, that should have been, I didn't elaborate enough on this, but when I didn't propose the data, so I have the data, but when I saw the robot evolving, you can see that the behavior of just after being attacked, the robot fleeing to stay to the nest was also interesting to observe.
Very interesting, yes. The other thing is, you mentioned predictive processing models. You talked about them a bit in chapter 6, and you referenced Kiverstein's paper and the free energy principle that Feng and Zheng used, but you didn't really bring it into the models very much, and I wondered if you thought it was implicit in your model or it's a later development.
I think that it's not something that we built mostly on. It's a feature that I observed and I wanted to highlight as a part of the literature, but it should be a further later development of our model to have full integration of free energy.
Yes, I mean, it's not obvious how one would do it, but you're certainly in a good position to be thinking about it and proposing something. Thank you very much.
Thank you.
Thank you, Amanda. So we can continue with Jeffrey KRICHMAR from University of California.
Yes, Luis, wonderful work. I really love the way you kept on building on the model as you went forward. So great body of work. So a lot of my questions been asked and answered beforehand, but a few things. So the one where you have a chapter 4 where you introduce cortisol. So can you talk a little bit more about the stress response, like what the robot is doing when the cortisol level increases and it's kicking its autonomic system, and maybe walk through slide 43, because that complicated with the axes of that kind of triangle where you're trying to keep within there. But first, talk a little bit about the stress response.
Yes, basically we worked to stress the idea was that as we have different affective hormones and hormonal perception, we still wanted to have things that affect motor strength. So the idea is stress is related to both internal perception and external perception, but we wanted to, based on what we had in literature, to have this feature in biology where stress affects the salience of environmental cues. So stress makes you experience stronger the environment. So the more you are stressed, the more you see predators, the more you experience and you detect predators, and also the more you detect and you are able to perceive the resources on the ground. So that says to avoid more, but also go more to resources. So that was this impact that we wanted to have for stress. And if I go to slide 43,
wait, before you go,
yeah.
on that point, so how did you increase the ability to perceive things, and how is that realized in the robot?
Yeah, so basically we have resources are detected using the IR ground sensors of the robot. So what we did is that IR ground sensors are responsible to detect a range of pattern of textures of the resources. So we have resources of different textures in this specific model. So what we had is we could reduce or increase the range that are detected, that are visible for the robot. So we increase the range so robot can affect, and we also reinforce the mathematically the Q signal. So we had a twofold impact. So first on the directly the IR the sensor perception, and then on the Q value. That's the twofold impact that we computed.
Okay, thank you. Great, that helps. Yeah, let's look at 43 and just kind of explain what I'm seeing here. What are the axes meaning, and what does it mean to be within that triangle?
Of course. So if you look at in detail, you get these two axis schema. First axis is the deficit of glucose, one of the internal physiological variable, and the second axis is the deficit of temperature. You get the starting point, which is 050, so deficits are all increased at 050 birth. So if you go in one side, in only one direction, it means that you increase deficit in a specific variable. And if you go up in both corners, it means that you both deficit increase. So that means that you have a lack of survival rate. So we have this triangle that highlights like a permitted survival range, where you know that both deficits are maintained in a correct phase. And that's what also I wanted to show and highlight in specific in this area, is that the behavior do activity cycles that impact in this deficit. So when you get A, you have an increase of a deficit, and B is reducing of the same deficit. So basically, it's just a combination of these triangles that represent the different behavior. Deficit increase, so you decrease it by consuming resources, but increase, you reduce it. So that's why it was important for us to see that without cortisol, the more you read, the more the time has spent. You have quite time when evolving your own time where you go out of the permitted space, while with you don't. And if you add this negative feedback, you see that in the end of the experiment, you finish with a lower deficit than the one you started the experiment with, which is also the main difference that with cortisol only, where you finish there with quite similar physiological space than you started the experiment with.
Okay. Oh, very nice. Yeah, I get it now. And then what defines the vertices of this triangle?
Sorry?
The vertices of these triangles. What are these the ideal? Yeah. How are those decided on?
Yeah, basically the first is 00, ideal value. Then you get 065, 05, and 05, 065, which means that when you have a deficit which is above 065 for each one, you get you are really threatened to die soon. And in comparison, when you are maintaining between this, so these shapes are geographically designed as a good space, but also have been empirically studied, and it's rare to have a scenario where you cross the boundaries and you survive. So that's why I selected this one, which I found interesting because it survived after, but it's really rare. In most of the cases, when you cross either one boundary or the other, or the last one, the robot will die from lack of a lack of an internal variable.
Okay, got it. Thank you. Now switching to chapter 5, I was curious why did you introduce spiking neurons in this? Was there an advantage to having spiking neurons? Because everything else could have been done with rate type of neurons. So
yeah, first one as a first thought we wanted to do some collaboration more with different scientists of the lab. So we wanted to study and to propose with different colleagues a new model. I wanted to propose a new tactile framework, which was the one that we proposed for mechanoception and sleep cloud. And we had a colleague that has a network model, but no input data to put in. So basically, when we study why spiking network is interesting. We see that you get memory recall. So even when there is no signal, spikes are activated. And that's a feature that we still not use for the moment, but can be really used because if you have a navigation algorithm and you get every time some spike that can give you like some shakiness and some variability in the response to the environment, so you're not full white. And also I wanted to have a first step to learn embodied sensory representation. And that was the idea that we also proposed to have like this weight connectivity platform that allows us to have this sensory representation. That's why we wanted to use this specific model to have like this temporal dynamics with the spiking part and also the weight connectivity in the end.
Okay, but I mean, you could still get variability with non-spiking models, and certainly the connectivity learning, the connections with non-spiking. Was there something about the temporal aspect, the timing, or maybe the DT, because it's 100 at 100 hertz versus what was the 25 hertz for the rest of your model? Was there something special about that? Because then that takes advantage of the spiking elements.
Yeah, we wanted to, as the idea was also to integrate only biologically inspired features in our model. Spiking neural network is like the most biologically inspired neural network, so that also leads us to our idea to build using this biologically feature. The temporal dynamic interested us, and this idea of recall of the neuron was something that really interested me to use in future models. So I wanted to build these steps to have the ability to have.
Okay. Yeah, fair enough. Okay, great. Then chapter 6, maybe this is a comment, but I didn't really find this a social context. You had one embodied agent. There were multiple predators, but that's just a more stressful, challenging environment. Why do you mean by social context in this?
Yeah, what we meant was a social context with relationships to other agents, which are predators. So I think that's also what we wanted to highlight as a perspective of this work, that we only study relation to other agents as threats, as something negative. And in future work, it should be interesting to also have a positive other agents in the arena. So that's why we put it social context in the idea that you relate to threatful, but predator, but still a social context because interaction with others, but only negative, and we should in the future add a positive context.
Actually, just for speculation, let's say you had two agents with the model of the pain modulation. What do you think would happen? Would they interact somehow?
Yeah, that should be interesting. For the moment, they are not able. That's not a feature to discriminate and separate positive contact to negative contact. So I think that both engines will interact with each other as if they were predators to each other. So we need to build and add some new blocks to our model to be able to separate good agents to bad agents for respectively for each perspective. So I think that they will be compared to bigger predators because the predator agents that we use are timidos that are smaller, so should have like more predators.
Okay. Yeah, and then just a couple more general things. One is Nadia brought up both these really important points, but I wanted to press you a little bit on the contribution to robots. So, what would there be a benefit if you put this model on some field robots that were doing some practical applications? And what do you think that would be?
I think that the sensory field approach could be a good approach to add in robots. That, for example, if you are a robotic agent in a warehouse that needs to evolve with many other robotic agents in a warehouse to select tasks, having this avoidance algorithm, this pain modulation could be an interesting feature to have, for example, in a warehouse where multiple agents need to evolve in the same place. I think that could be one application to increase, but you will have to replace the motivation with a motivation that fits the company needs to pick up a package, for example.
Yeah, I agree. And to Nadia's point, you don't have to comment now, but I do think you have a lot of advantages here for understanding, pain, how it's coped with, disorders, things like that, because you have a really great model set up. So give that some thought going in the future. And then to Mehdi's point, compared to like most models of this sort, your model has robots, which gives you the advantage to look at emergent behavior. So also, I think there are ways to actually watch the behavior, setting up video cameras. I know your robots don't have a sense of where they are in that space, but still you could, there's probably some interesting emergent behaviors of the regions that they're staying in. So you may want to think about that in the future work about how to actually observe some of the emergent behaviors and report them, because I think you'll find some really interesting stuff with this type of modeling.
I agree with you. I think in future experiments, collecting more data, probably be the one to observe empirically the emergent behavior should be an important part of future work.
Great. Yeah, well, thank you very much for answering all the questions and beautiful report and beautiful presentation. So I'll give it over to the next person.
Thank you.
Thank you, Jeffrey. So we continue with the examination. Marwen.
Thank you. I'll try to speak loud so that you can. Or we can. Okay. Thank you. So I would like to first thank you for inviting me in this committee. It's really a pleasure and an honor to be here, especially with Lola and Jeff, who were in my thesis committee a few years ago, and with other esteemed colleagues. So real pleasure to be here. And I would like to congratulate you for a very nice presentation and thought-provoking work. So I'll start with quite a general question. And I would like to hear your thoughts about, after these 3 years, what would you do differently if you had the chance to redo your thesis from scratch?
Yeah, I think that I would probably provide more studies with more steps between each iteration of the model, because I think it has been pointed, and it's really relevant to say that with this much dynamics, when you change too much things, you can compare. I think that I would also lose less time trying to spread too much, and we focus more on what has been the guideline of the thesis and this presentation in the final, and that will probably help me, because in the first time when you search a PhD, you have like a wide range of possibilities, and you encounter that doing the experiment, collecting the data, having the correct state of the art to support your thesis is quite hard. So I would say that I would probably have focused more on this field, and I would probably be able to make it longer. And what I think is the miss is what I wanted to have in this thesis, in the idea is to build this model to study the dysfunctionalities. And by missing all these parts in the early, I would have been able probably to run some experiment on dysmorphia, which are a mechanism which I'm really interested in phantom pain, in chronic pain, which are mechanisms that I think really miss of models. And I think that they would have been great contribution to the field. So
very interesting. Thank you. Now maybe a little bit more, let's say, technical questions about some of the equations you were using. So Mehdi asked earlier about the motivation equation. I understand the history of why you chose this. I was wondering if you or someone else, if you're aware of that, analyzed a little bit the behavior generated by this equation. I'm especially wondering, what are situations where it's really interesting to have this term where you multiply the deficit by the Q?
Yeah, actually, the paper that we use as reference for this equation by Toby Tyrrell is a wide study of how different action selection model can be used, and that's within this action selection model that he proposed this equation. So he has a quite interesting study about the difference. But I would say also more than the motivation equation itself, what could be interesting to have other model that we use winner-take-all to select after the motivation computation which behavior selected the best is the same. It was a point of view to select winner-take-all for all of architecture to not add everything that changed in the dynamic, but having voting base, having other mechanism to select the motivation, the behavior, and the greater motivation that need to be activated could also be an addition to change the dynamic of the model.
Okay, interesting, because in your answer you touched upon a question that I was thinking about asking, which is what if you did something else rather than winner-take-all? So that's interesting. And then related to in general, the equations related to hormones, I was wondering what was the process that led to these types of equations. Are they imposed, inherited? Are they really well thought and designed to serve a certain purpose with some criterion in mind?
Yeah, that's an inheritance first, because that's been we are a field where work is done by iteration by many other sciences before. So we work on architecture, and by many other fields we explore. And so we take an architecture, we try to explore in one direction what can this architecture bring us. So this kind of equation for hormonal has been used by both Matthew Lewis, by Orlando Villagarcia, by Imran Khan. So that they explored using this, but they explored different perspectives. So mine was to study how pain can affect model selection. So I think my aim was not to model the artificial hormone, but to use this to model how pain can affect model selection.
Okay. Okay, and now related to peripersonal space, which is something that you talk about a few times in your presentation and your thesis manuscript. I mean, as you know, I worked on peripersonal space in my thesis. I will seize the opportunity to ask you to elaborate more, because I was a bit frustrated that I didn't find enough material about this in your manuscript, and maybe more specifically. Okay, so maybe first, how do you think your work relates to this topic?
Yeah, I think that the first of our idea was not to relate to peripersonal space. It was the idea of we have this robotic platform. How can we reconstruct complex sensory inputs? How can we have nociception without adding new receptors? So you have two choices. You add new receptors, which was not what we wanted to do, or you use the actual one. So using the proximity information, you work on the sensory on the peripersonal space. So the idea was first starting from the lack of data from the robot. How can we reconstruct? So from this, I read some references, and I think it's one reference in the thesis manuscript. Your work on the peripersonal space, and we wanted to elaborate more and to have this idea of it's an extension of, it's really seen as an extension of the body, and that's why we compute it as like it's an elastic material, like a physical blob that is not physical because it's only sensory. So that's I think a transformation of how we can use peripersonal space to give more information from very limited data. But
so with this idea in mind, I I see a lot of overlap, let's say, and common ideas with your work and what I did a few years ago, and especially this kind of elastic plastic idea of this representation, what you have also in your sensory field. And to elaborate a little bit more, so one thing that was proposed in our previous work was the idea that peripersonal space is the space where it's safe to act. So it's not only the safe, comfortable area around you, but it's also the reachable area where you can actually behave. So more active than passive. And I was wondering how what you did relates to that, if you can elaborate a little bit.
Yeah, I think that what we did also in the navigation algorithm can relate to this, because if you look at peripersonal space as something which you try to minimize deformation, that means that you want to have like non-harmful stimuli, non-noxious stimuli within your peripersonal space. So trying to reduce and to minimize the deformation of the peripersonal space can be seen as a way to have only a positive bond. And in a new model, because we said that what we can do if you have positive agent, we could tolerate positive agent within this sensory field and neglect negative agent. But that's not something that we implemented, but I think that's a possibility of the model.
Indeed, I agree. Then I had a question that came to my mind when I saw a graph representing your architecture. Is on page 50 on your manuscript. I think it's chapter 350. But anyways, you will understand which one I'm talking about when I ask you my question, maybe. Because it was pretty obvious on the graph that there's an asymmetry between pain and pleasure. Let me know if you know which figure I'm talking about.
Okay.
I think it's either chapter 3 or 4. And I was wondering if that was something that you are claiming, in the sense that you think that there is indeed something more important about how we process pain that requires an architecture to address it more, or if it's kind of a byproduct of the fact that your thesis is working more on pain than pleasure, so you didn't really work on connecting pleasure.
Without the graph, I think I can understand and relate to Mehdi. Yeah, no, the title of the thesis is Pain and Pleasure, but experimenting like more interest, and I found that the mechanism related to pain are quite more interesting to integrate. I think so that's starting from this idea that both are really important mechanisms. We focused on pain and we try to elaborate more on pain. So that's why there is pleasure in the first section, and we to minimize the dynamic of the model, we reduce it in the next section and chapter. So I think because the pain mechanism, there are features for avoidance, for recovery, for even the fight or flight behavior are really interesting. So that's why I even if in the first study both are present, in the next section and next chapter, I wanted to give quite more focus on pain, because I think that's really missing. Because we study a lot of positive context in robotics, but pain not so much in the literature. So I think that proposing this new model was interesting and a novelty in the field.
Okay. And maybe one last question, if I have time. Yeah, quick question. In your cortisol model, I was wondering if you had thought about how it could inform or contribute to health research.
I think that's the question of it's still in the thesis title. I think we propose to have this mechanism both for improving robotic platform and robotic navigation, robotic action selection architecture, action selection models, but also to provide models to other scientists. So we did it in the first chapter, which led to a presentation in a workshop that we did in common with Amanda about this question of adaptive value of pain. But I think that many of these models can be with interdisciplinary research, collaboration with other researchers, be used or be adapted to be used to give better understanding health studies. That is not something that has been done for every part of the study.
Thank you very much.
Thanks. Thank you, Marwen. So, because I will change my role from president jury to examinator, so I have one or two maybe questions. I'm not specialist in robotics, but it was very interesting in the research we've done and the presentation. So I have maybe one question about the pain, and you said that there is a threshold that you fix or compute on the pain, threshold, effect threshold of you. So my question is about that, maybe to make a link between this threshold of pain and the tolerance. Is there is a link between the tolerance?
You mean the sensory field?
In one of the slides you have put threshold of.
Yeah. I think so.
Which I well understand, but yeah, this one. Threshold effect, we see pain. So my question is, do you think that it's something close to the tolerance? I mean, that you have to tolerate the pain, like in some level.
I think that's not. That was this threshold effect was part of the computational model proposed by Maniscalco and Infantino that we do not repeat or include in our specific model. I think that another example of tolerance that we have, which I can show in 10 seconds, is in this specific model. In this video, you can see that you have a different threshold, different areas for the sensory field. So in the yellow part, you have the mechanoreceptors, and because in the skin you have different dermis, we propose to have like another threshold for the nociceptor compute. So yeah, that means that you can have some contacts that are not noxious. So that is for us a mechanism of tolerance for some type of stimuli. So you can feel a touch, but it's not harmful.
Maybe one more question, because it was thought that the robot can die. Yeah. So I was wondering if it means that the robot also born or not. Because if you were someone to die, there should need to born before.
Yeah.
So do you have a date, a born date, the date of birth?
No, we should, but no.
You can define, give a definition.
We actually, yeah, it could be in the sense that when you start the experiment, the robot has a values of start of its internal physiology. So we can say that in early life you don't have full life, full energy, and you need to construct it. We start most of our experiments with mid-level for each variable, but that could be an interesting feature because you can die poorly with a lack of physiology, and that could improve also the developmental trajectories.
And then just last question about the perspectives. So maybe let's say in the future you can maybe have a funding to found the internship or master internship. Which kind of subject you can do it?
To propose to
master internship, for example, if tomorrow write a subject for the master internship for 6 months, let's say.
Yeah, I think that for example, a navigation comparison could be proposed in a master internship, or the question of the evaluation of the frugality of the cost. Comparing our model to different approach could be also an internship that for 6 months you get the models, you need to compare them to other part of the literature. That could be, I think, positive.
More questions. So Lola, if you have some remarks.
Yeah, I won't ask any questions.
Yes.
But maybe just tell a little bit the story of the thesis. So we met 4 years ago when we was doing his master. He decided to do one of the projects I suggested, and then continue doing an internship. And then was crazy enough to continue a PhD on this topic. And I must say, all the way through for these 4 years, he's been a very creative person, a very engaged person, very fun to work with. he has lots of ideas. He has too many ideas. That was one of the discussions we kept having. Well, it's been a pleasure to work with you, and I am glad that you're going to continue for a few months. So thank you for all this work, all the fun, all the agreements and disagreements that we've had, and you've been extremely hardworking and very creative. So thank you.
Thank you. So, if there are no more questions, we can ask in the room. There are PhD questions. Okay, the doctor can take history. Thank you. So we finish with this part. Now the jury will deliberate. So we'll stay in the room.
Yeah, maybe we stay in the room, and we're gonna move to the other link that Louis sent, and I'm going to start.
I go out from here and go in the other link.
Yeah.
Okay, see you soon.
Oh, wait,
Hopefully
on
in
the
the
Zoom
other
link.
place.
Yeah.
The Zoom link or the Teams link, the other one?
I have no ID for the moment.
Yeah,
Searching.
which link was it?
Don't know.
Okay, I'll try the team. Well, no, the Teams one was, I guess we'll try Zoom.
So let me search too. Yeah, that's a Zoom one. Zoom. Yeah.
Okay, I'll be right back then.
See you there.
Addressed in his thesis, as well as the innovative solutions he developed. The present research work had a strong interdisciplinary approach combining AI, robotics, computational modeling, emotional modeling, animal behavior, and physiology. During the discussion session, the jury members posed various questions from fundamental aspects to experimental details. Mr. L'Haridon's ability to respond precisely and contextualize the limitation and potential improvements of the proposed approaches was particularly appreciated. This demonstrated his scientific maturity and a clear vision of the impact of his research contributions. The jury appreciated the coherence, the originality, and the rigor of his work, which stands out for its significant contributions to the modeling and understanding of the pain in biological organisms, as well as in the fields of neurorobotics and artificial intelligence. The perspectives opened by his research in these areas offer innovative perspectives for future applications in various contexts. For all these reasons, the jury unanimously awarded Mr. Louis L'Haridon the degree of a doctor from Cergy Paris University in the specialty of STIC, Information and Communication Science and Technology. Congratulations.
Thank you.
But you have also enjoyed
The oath.
Yeah.
sermon.
Je peux le faire en français?
To you.
Bien. En présence de mes pairs, parvenus à l'issue de mon doctorat en STIC, sciences et technologies de l'information et de la communication, et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. I would like to deeply thank the member of the jury who accepted to evaluate this work all around the world by being so early for you, Jeff. Thank you very much for joining. Amanda, Nadia, Marwen, Mehdi, Nistor, and Lola, deeply like to thank you for participating to this jury. I would like to thank the member of the lab. I will maybe switch in French from now. Je voudrais remercier les membres du laboratoire ETIS, de l'équipe neuro, que ce soit les enseignants-chercheurs, les membres permanents qui m'ont accompagné dans toute cette thèse, mes collègues doctorants, ceux de bureau, ceux avec qui j'ai collaboré, écrit des articles, ceux qui sont là, ceux qui ne sont pas là, ceux qui préparent aussi leur thèse, ceux qui m'ont aidé dans la préparation de cette soutenance. Merci Hervé. Je voudrais te remercier, Lola, de m'avoir donné l'opportunité de faire cette thèse. Quand je suis arrivé à la fac, je n'étais pas certain de vouloir aller jusqu'au bout et de vouloir aller jusqu'à faire un doctorat, mais quand j'ai vu le sujet que tu m'as proposé et la collaboration qu'on a eue, j'ai aucun regret. Je pense que tu m'as aidé du début à la fin à me dépasser, à aller plus loin que ce que je pensais être capable. Tu m'as cadré et m'a empêché de partir dans toutes les directions, ce qui aurait probablement rendu ce manuscrit, cette soutenance radicalement différente et plus diffuse et confuse. Donc merci beaucoup de cet accompagnement et puis aussi du côté humain et de l'accompagnement que tu as eu tout du long. J'ai vraiment apprécié nos échanges scientifiques, nos échanges aussi personnels, et merci de continuer à vouloir travailler avec moi quelques mois de plus après cette thèse, qui fait que je peux passer aussi des vacances plus sereines. Donc, et c'est aussi vraiment un plaisir de pouvoir continuer ces recherches, que je suis fier du travail qu'on accomplit et de la manière dont on contribue. Je trouve que c'est une contribution utile et originale. Donc merci beaucoup. Je remercie beaucoup voilà, encore une fois à tous mes collègues, pensée spéciale à Raphaël, avec qui j'ai collaboré, qui est à distance ce soir et qui on a écrit cet article, qui pour moi m'a aussi beaucoup inspiré, m'a aidé à donner une trajectoire à la fin de cette thèse et aux futurs impacts. Baljinder, Mehdi, Hervé, tous ceux qui ont voilà, travaillé à mes côtés. Je voudrais remercier toute la communauté scientifique et puis particulièrement Pierre-Andry, sans qui je pense que je ne serais pas arrivé à Cergy par l'université. Et c'est lui qui, il y a 9 ans maintenant, m'a fait visiter le laboratoire et m'a dit que c'était possible. Et début de ma thèse, je donne une phrase d'Irène Joliot-Curie qui dit que quand on est un savant dans son laboratoire, on est un peu comme un enfant qui voit les choses magiques du monde et les phénomènes s'évertuer devant nous. Et c'est un peu ce que je ressens en étant dans un laboratoire. Et donc, merci à Pierre, merci à tous les enseignants qui, à CY, à l'UCP puis à CY, dans ce magnifique service public d'enseignement supérieur et de recherche, m'ont permis à faible coût d'apprendre sans compter les heures et de me progresser. Et j'ai été aussi très engagé dans cette fac, et c'est pour ça que je pense qu'elle a forgé beaucoup la manière dont j'ai été. Jusqu'à la moitié de ma thèse, j'en étais encore le représentant étudiant. Donc merci pour tous ceux qui m'ont accompagné dans tout ça. Merci à mes collègues d'une autre vie qui sont aussi là et qui me regardent. Merci à mes amis. Ça me touche que vous soyez tous là et là. Je pense qu'il y en a beaucoup avec qui la vie a commencé avant, mais on s'est retrouvés ici. Il y en a beaucoup qui sont allés ailleurs étudier, mais vous avoir à mes côtés aujourd'hui, ça me touche. Avoir aussi, vous avoir tous ceux de Cergy qui sont là et qui on a fait toutes ces années ici, vous voir ici pour le dernier survivant à l'université, c'est aussi quelque chose qui me touche beaucoup. Je pense à tous ces moments qu'on a eus dans le bâtiment, et je pense que si vous n'aviez pas été là, moi j'aurais été incapable d'aller aussi loin dans ce parcours universitaire. Merci à tous ceux qui sont venus aussi, amis de la famille, de votre présence. Ça me touche beaucoup à vos côtés. Je voudrais remercier mes grands-parents de Bretagne qui me regardent à distance parce qu'ils n'ont pas pu venir, mais je sais qu'ils me regardent, ma mamie, ma grande-tante, mon papy qui n'est plus là, mais dont je sais qui me regarde. J'aimerais remercier du fond du cœur mes frères, mes belles-sœurs, mes neveux, mes nièces, mon filleul, parce que c'est aussi avoir un entourage familial riche qui fait que même quand on doute de soi, on arrive à aller au bout. Et puis, évidemment, remercier ma mère et mon père, sans qui rien de tout ça n'aurait été envisageable et qui m'ont aidé à me dépasser, aller au bout et à arriver au bout de cette expérience académique qui a commencé à 3 ans dans une école maternelle quelques kilomètres plus haut, qui se termine ici par ce doctorat. Donc, merci sincèrement à toutes et tous. Et puis merci de votre présence qui me touche, et je tâcherai de pouvoir continuer à chercher et puis à exprimer, à aider, à comprendre, parce que je pense que ce qu'on fait, ça aide, et je l'ai écrit dans ma thèse, la recherche, la science, c'est ce qui combat l'obscurantisme et ce qui nous aide dans un monde de plus en plus noir à essayer de laisser un peu de lumière. Et si à notre humble petite échelle, on arrive à y contribuer, je pense que c'est la fierté, c'est le combat d'une vie. Donc, merci à tous et tous pour ça.